Dimitri, what file has the densities in it?
What?
What file in VASP showed the density? Like each MO's density?
Or church?
Watch.
somewhere sharply at 5?
Yeah. I teach at 5. I'm just going through the figures though, so I'm not going through the
Thank you.
text.
I admire how cold-blooded you are.
Why?
I'm always late for some meetings, but I start being nervous like half an hour before it starts.
No, I just have to walk over a building and up 3 floors.
Just cold-blooded.
I thought you were talking about this. Even though I've noticed that a lot of you guys as groups make the font size very small. Like if you shrink this,
Mhm.
this won't be legible.
Yep. Thank you for noticing it, yes. I was talking about your work.
Oh no, it's not only his. Oh, Landon. Oh, I did it all over the place. I even did exclamate. Yeah. I don't see it though. Yeah, these are way. This. Who's gonna be able to see that?
I noticed it, but I know someone's just gonna comment on it in the next revision anyway, so I'll just leave it for the next revision.
So yours is let the reviewers pick on that, so they don't pick on this.
It's worked in the past.
You know.
I think there's one manuscript I put in, it's like, I think the biggest thing they criticized was my usage of where. The wrong usage, like throughout the entire thing.
Wait.
I use WHERE instead of WERE. For like every time I should have used WERE.
Oh.
It's like the spatial where instead
Yeah,
of
yeah.
like were. So it was like.
Yeah, that's why I was like, where?
Where were,
It's
yeah.
not like they or there.
Where were, that's what I meant.
Okay.
Quick comment, because I can forget. I like your abbreviations, but MRT probably is not the best one because it's like magnetic resonance tomography.
what is the index on R? Is it IIJJ?
Oh, sorry.
So Aaron has IIJJ. This one has IJIJ. Which one's correct?
Aaron is in business for a longer time, therefore everything he writes is more reliable. The IIJJ is population relaxation, IJIJ is dephasing.
Alright, IIJ.
Thanks for good catch. I was looking through it and I missed it.
I guess the thing is, send it to people that don't do it, and you get better reviews. Yeah, I was just putting them in a pile.
London will come and will write over because you don't have enough copies for everyone.
Oh, good thing I used red.
Many thanks.
Yeah.
See you later.
Yeah.
Yeah, I filled this in first and then everything around that.
C will correspond with this transition, and explode corresponds with this transition.
I suppose I should have.
Make separate for experts.
Okay.
It is very good if you do like this, all the transitions contribute to the same and these two data sets are consistent. They are assumed to be generally the same mix. And the line is experimental observation for two types. Either the anchor or the coincide, it just good luck. We can I've got an idea for the contents. Here. So if you take this one, compare it with this one, this one, here, it will take the contents. If you do the
No, I kind of, so it's computed.
computed and experimental, and remove this one.
Oh, right. Okay, yeah. Yeah, I just haven't updated that one because I keep forgetting to pull a better spectra from the computer at the lab.
I'm criticizing myself for that. Too much pressure. We better accelerate looks closer to.
I always imagine there should be some way. Obviously, there's a way you should would make sense to plot the MD and PL over the same spectrum computer from the MATLAB, just to get more figures on one table.
We would need to combine electrodynamics, photorenaissance, and DPM into one methodology. Right now, it is in nature simultaneous synchronization and motion because we kind of separate and separate things. This is very rough approximation. So it's we include date.
the PL, but that's basically the MDPL method is.
It's missing factors that within transition energy oscillates and it corresponds to exploring different regions of potential intercepts. So in some sense it is a potential Lagrange progression. Transit factor going because
Mm-hmm.
each time step the DPL the oscillator flux is different. So it also has modulation of the oscillator strings by
Mm-hmm.
so there are two additional effects. If you strange if you include these effects coming from room, do it from the rest of the other, the electronic dynamics includes optical transitions from excited to excited. They're not super important. They're even important. But since you keep them in the thing is fairly universal. If it's not only a calculation, it is an experimental fact. The hallucination neutron only from one split universe. Where here, they more discrete structure. So, in addition to this, it gives strong structure. And this is completely absent in the indicator. So, you admit that these two methods are both of them incompatible, but they kind of cover different aspects of the system, of the nature of the problems. And ideally, one of them is something universal. Universal is not always good. This aspect of the good of times, which will get more interesting. Just the people that you need to ask before there is some justification for doing this.
Yeah, and how you? Here's so which color are you using for writing?
I don't know.
Because
I have multiple colors.
red is already reserved. The I was sitting here and everything is in red. But if you do second layer with different color.
What about blue?
Perfect. I have pink.
I think I do too, actually. Where's Daniel?
Who?
Daniel?
I'm not sure if he is free at this time. He may need to key. Be a majority. Yeah, probably you need to send all other works to him and demand that he will grade.
Yeah. Definition.
something for this meeting is just to play this. Well, if you are really angry, please continue. I will try to be not very loud, not to disturb you. But if you're interested to participate in discussion, you will. So, if anyone wants to be advocate or prosecutor or this voting, then I will start. So, well, it was an agreement and understanding that the result section is a preliminary sketch, and there is nothing wrong, but one can probably optimize the way how it is goes. First, the description of atomistic model can belong to the results. It would be very reasonable. I don't know in what portion you removed the figure with atomistic models.
I figured that would go better in the introduction. Just so that people understand what it is that,
Okay, you
I don't know.
see free choice. But here it looks that you are relying only on the localization of orbitals, which is correct. It is a good proof that photoexcitation will sooner or later result in charge separation. But if you talk to a practical engineer, you will not sell orbitals. So, what an electrochemist who just does curves. But if you tell that there are two factors, one is localization of orbitals, and another is offsets of band edges, it will be kind of redundant. Both pieces of information tell the same story, but the offset of band edges is something very general that a much broader audience would agree on. And I don't know, you have experience in TA a lot. So you imagine someone not from science, from nursing, freshman, and try to write it in such a way that she can understand. So it's not nothing about to details. The statement that perovskite is the main absorber is probably correct, but logically it's not enough for proof. Well, we're not hunting literal mathematical proof, but when it's to add something more, like here, if we would show orbitals that contribute most to highest oscillator strength transition, this and you will see that they are localized in the perovskite. This would be probably better proof. It's not suggestion to follow, it's just ideas to consider. Just go and write something about each figure.
That's pretty much what I was doing.
Okay. Here, I just try to verbalize things about factor 1, factor 2, and they both support the same conclusion that hydroxy will give charge transfer and acetate will not. Anyone wanted to make comments to defend work of London or persecute it?
You can just be a little more specific for binding energy.
Oh yeah, for sure. I just like, I had that other figure and I was like, I should throw this in there somewhere. So it's like,
Maybe I just mentioned binding of what to what.
Yeah.
Because you have ligands on clusters.
right.
All sorts of stuff binding.
So in the final paper, I would imagine that I don't think I'm gonna have the binding energies on that figure.
Yeah.
That's more like post.
In your text, you mentioned values, but you didn't interpret. Like, binding energies are different, so what?
Yeah.
I think you could leave them there because it shows the difference between the two functional groups. Because you would expect the OH to have stronger binding than the CH3 group. So
It goes along intuitive expectations. I don't remember if I was writing it, but one can draw bonds between
Yeah.
them.
I'm making that figure right now on that. And like actually putting the the A, B, and C and D like in decent spots instead of just having it thrown in somewhere.
Well, probably it is what everyone commented last time, but I did this comments in the middle of the week. We are not exciting to UV, so.
Yeah. So I did that, I guess, and I'm also working on the PDOS right now. The isopropyl one did not. Well, maybe it's done now, but didn't want to start.
Do you plan to introduce notation and underline it in the figure in the visual form? Here is the green box is higher than yellow, and here yellow is higher than green.
Yeah, I can do that.
So the colors are to support the Bison nation.
Yeah, didn't know what colors to make it, so I was like, I'll go.
Put little Bison here. Editor will love it.
Didn't want to use red and blue because I was already using that for other stuff, and figured that might get confusing.
if I wanted to be picky, you for me should be like bending a little bit. That first panel.
What?
This is Fermi energy.
Yeah,
It should be-
bending. Yeah.
So, with this one, do you think that I should just get rid of that like 0 to 3 range? And just like verbally say that there are no.
Yeah. Well, maybe 0 to 2 to if you like cut it here where there is a little tail, it will be suspicious.
Right, but like, should I just get rid of all that white space and then just not have all the transition details in there, I guess?
Yeah. And it would be more standard to have this information as maybe additional table rather than inside the figure. I didn't remember literally, but when I was reading, I went through your data, and it looks like there are champion transitions. There's specific pairs of orbitals that give largest contribution to oscillator strengths, and they're good candidate to also show. And one can organize it differently, either place it into a separate figure or as insets in the DOS. Because when publishing, one can ask to assign the whole page for the figure and then make density of states at the bottom and then more white space at the top and make little connections and put several orbitals for each figure. But it's artistic thing.
You're saying like show the relaxation path like in orbitals? I guess I'm not sure. Or just like the two orbitals.
So right now you are showing two orbitals.
Yep.
But you can show more, like maybe arrow going from here into there, and here one more, another pair of orbitals. Like this one is final, and this one will be initial,
Okay.
or put excitation promotes carriers. Femtosecond?
Should that be picoseconds or femtoseconds? I genuinely don't know.
I got inverse femtoseconds.
Okay.
If it will be so small number in inverse picoseconds, relaxation would never happen. And if you were reading were you already grading the work by error? So she kind of explained this general trends. I understand that often these trends may grade one paper to another one, but it's natural and repeatable for us, but many side people will learn, you will be teacher of negative relaxation for them, so don't skip this.
Okay.
So it's like off main subdiagonal. The main diagonal is 0, subdiagonal is non-zero. Okay? And as far as we go out away from the diagonal, it decreases. So in some sort of case, another way to record the gap. Just observe what is seen in the figure. Okay?
It's been restricted.
Yes. They are.
So there is no spin orbit here.
Right.
Okay, that's fine. If you would have spin orbit here, then what would you do in the next thing? Now you have expansion test. Well, it's kind of little discovery that they get occupied one after another. That there is no jump over the head of a neighbor, right? Subsequent, and it's worth mentioning. And it also agrees with shape of Redfield tangent. Oh, this is true. Well, if once one can write 10 pages composition about these figures, there are so many features to describe. Like here it's interesting that it happens not simultaneously, but there is a charge transfer. And if it's an opposite direction. Like here we expect the electron goes to the index A and Hall stays on the perovskite. Here it goes opposite direction. And if one would put contacts that will pull charge quickly enough, it may work as a solar cell or work in opposite direction. If one takes the charge away, well, it's not visible. Also, someone Levay asked which version.
Oh, yeah. I'm gonna rework all the figures.
It looks like that simulation cell is chosen this way, that this is 0. So in addition to referring to figures, one can just tell if z greater than 0 is accepted, if more than 0 is Did you work on the comment about the tweaking the colors?
But the what?
Tweaking the colors.
Oh,
to make the
yeah,
background
if I
green.
just set the same range between them, then they should
Yeah,
at least match each
if
other.
the minimum and maximum, then it will zero the difference.
Yeah, because I tried to. I was just looking at like the different color schemes, I guess, when I was trying to do that originally.
But it's not also a color scheme. It's one needs to add artificial data points, so that
Yeah,
it
like algorithm.
ranges homogeneously
Mm.
through the colors.
And that offset, I can't remember off the top of my head what that was about, but I feel like there was a reason for that.
Well, it's very strange.
Yeah.
Probably you've got comments from other group members. Do you remember it in Landon's work?
Yeah, something's off. Like even the blue dots and all that, those should be checked as tied by like an EV.
So probably one can go over definitions of the x-axis once again, and the dissipated energy is difference between initial and final energy of carrier, right? And then if you excite it like from O to O plus 1, it will be almost 0. It will be not 1. There is no sub-gaps of 1 EV. Well, and also from home minus 1 to home will be like very small. Okay. Anyone wanted to give verbal comments, more verbal comments to Landon's work?
So once they combine figures 6 and 7.
Which ones are these?
Old 6 and 7 or new 6 and 7?
The dynamics figures.
Oh,
Those
okay,
two.
so yeah, you're saying.
Yeah, just plot them on top of each other. Because then that way you can,
Save space for x-axis.
that too. Then you can relate like that first, like, energy relaxation. Like that little, the longer existent state in the conduction band. You can relate that to the yellow features in the spatial. It'll be easier to line up like the time
Yeah.
that the events occur. Draw comparisons between them.
Okay. Any comments from Fatima? Maybe one?
I forgot.
Well, Daniel is not here now, but maybe we can chat a little, hoping that he will watch the recordings. Well, it's not clear why one uses the space filling stuff. Orthographic projection would work much better to cover this three-dimensional things, and one can describe in more details how the model is composed right in the caption, like telling that there is a alternating cesium rich and gold rich number of these layers. Yeah, it's we're missing Daniel here because everyone here in this audience, we were already discussing benefits of labeling the things because later on one can refer to the transitions. And same thing can be done for Daniel's work. Also comparing to what everyone is doing, I don't know, maybe labeling of SPD could make sense, or one could go with general like notations, but the difference of sets between different peaks can be good help in understanding of the peaks in absorption. And the white space is not needed, so one can focus on the reasonable range. Something general, I think it is, well, this is little technical details, but it also deals with Warpel Fatima. If we start absorbing from red to blue, from the gap to no gap, it could be reasonable to label peaks in the alphabetic order starting from the lowest transition. And instead of skipping them, label each of them. And Daniel may consider, if he watches this recording, to add a table to summarize these optical transitions and make connection between peaks for in the absorption spectra in transitions between features in density of states. So what several of us are seeing in the works is that for one, well, we understand that features in the density of states are not one orbital, it's just groups of orbitals with some degeneracy, and maybe some level of width. So not purely degenerate. But transitions between different groups of orbitals may have approximately the same transition energy and compute to the same feature in the absorption spectrum. And there is nothing wrong to mention it. We just we shouldn't expect that each transition between features will give a unique transition in the spectrum. Like two groups of transitions may result in one peak in the spectrum. Well, Daniel decided to show few orbitals, maybe for easier passage through the whole paper, but it may or may not work well. Maybe those are most important orbitals. I don't argue here, but to analyze them and make a connection between optical properties following from this pair of orbitals, and analysis of whether this pair of orbitals gives is dark or bright, one may consider to add this integrated one-dimensional peaks. And telling, well, here one can, even without analyzing the data, one can make conclusion that it's still a dark transition because they are localized inside and outside of the slab. But since the goal of this calculation is to make it efficient absorber and emitter, one probably may want to show another pair of orbitals that would give highest postulator strength. Please feel free to stop me and add comments if you had some. In caption figure 5, there is something that I don't understand. If Daniel would sit here, we would ask him to defend the statement. Like, what is the positive charge transfer? What is negative charge transfer? Maybe it's just figure of speech, like I'm positive. There is a charge transfer. But this looks like both of the orbitals, occupied and unoccupied, are localized in the slab. So these two are not expected to give any charge transfer. It's just optically bright pair of states that give optical transitions. And according to notation that Aaron was designing, if you were reading work of Aaron and his labeling in the density of states like SPD for electron and SP for hole, this pair of orbitals in Daniel's work would correspond as transition from S in hole manifold to P in the electron manifold, where this S, P, and D refer not to atomic wave functions but to envelope functions on the larger scale. It looks like Z range in this figure was not sufficient, so it was head section for each of these peaks. Therefore, they were of the same height. It's very unlikely that in numerical calculations several data will have the same value. It looks like just not sufficient range. If one would allow like twice or triple times bigger, they would have higher height aside from the band gap and a little more closer to band gap. Another, like Daniel, if you're watching these records, these captions are more like observations and information that analysis of the data, but one needs to insert introduction, description of what is shown for people who watch it for the first time.
So these calculations look like spin orbit.
It looks like spin orbit, but I'm not sure if Daniel recognizes it. So it was made with cooperative. So it is with all bells and whistles. Mm-hmm. So I just need to describe it.
Then is the ground state.
Hmm?
What about the ground state? Observables?
Could be mixed. If you ask this question to Daniel, it would be appreciated. For all of us, how did you recognize that those are spin orbit calculations?
Those two peaks that are like adjacent to each other.
Yep.
So I've only seen it in spin orbit.
Mm-hmm. Do you see it?
No.
Like if you look in panel B,
Yeah.
you have two peaks that are like the same height next to each other.
I mean, is it the fact that you got like 2 and then nothing and then 2 and then nothing and 2 and then nothing? Or like,
Not as much as nothing, because then like the really fast. Yeah, you have really fast transitions that are right next to each other, and then slower, and then it increases and slower again. And that's just due to two states having the same energy. So you have like a resonance condition between them.
so, okay.
So like this peak here,
Yeah.
so it's like HOMO to HOMO -1. And they have the same energy.
Aren't those always electric though? I guess I've never seen it not symmetry. I just assume that it always is, I guess, because like it's all based on the couplings, which is
It's
based on like overlap. I mean, it's not really a directional thing, I don't think. I mean, I could definitely be wrong, but
It might be the angle, but I think it looks like some of them aren't exactly the same. It could just be the angle though. Yeah, generally, it's like you see this, and then it dips down, and then I don't know, I've been dealing with like the past half year or 3/4 of a year now. So
Yeah. Well, because every time I see the Redfield tensor, it seems like you could just kind of slice it down the diagonal and you wouldn't lose any information because it's all
But-
symmetric
No,
across.
no, it's symmetric in respect to main diagonal, but here you see it's alternating. For if it would be without spin orbit, these gaps would be filled. It will be continuous.
Oh, okay. So it does have to do with the fact that there's gaps there.
Yes. See, if you have this alpha and beta,
Yeah.
there are transitions from between LUMO and LUMO plus 1, but there are also transitions from LUMO to LUMO with only spin flip. And Aaron can tell better, but one of them is really intense and another is less intense.
Okay.
Probably the one is degenerate is very intense. Right? And it's kind of signature that helps to identify.
Your call will be disconnected.
It's fine. That it is with spin orbit.
usually your spin restricted looks kind of like your density of states curve, or kind of like
Yeah, where it's
flattens
just kind of
out
like a continuous, wavy sort of a thing.
yeah, like near the homo lumo, like it decreases.
Yeah, yeah, it'll dip down right there,
But then for spinner ones, it's you even get the high peaks near the homo lumo
Okay.
gaps. Just because two states next to each other are always going to have fast transitions.
yeah.
Good. So anything else for Daniel? Well, I think this is also almost a standard thing, but for electrons in Daniel's system, it looks a little different compared to what we just seen in London's system. So for holes, it is subsequent transition, and in the electrons, it jumps over several neighbors. So it skips several states and they stay unoccupied. So it's interesting feature that one can notice in the captions and results and discuss in discussion. So for distribution of electron density as function of energy and time, one probably needs to introduce it, because how do readers know about it? And many readers do not read text; they just go immediately to figures. And same about space distribution. Okay, done with. Oh, and also Daniel has tables that can be summarized in the same way as most of us are doing. So summarizing rates as function of dissipated energy in graphical way. So we work off Fatima. Another screen. Yeah, one would expect that these transitions are defined. Maybe they will be introduced in the introduction, but it's very good to see them. In the second paragraph of results, one may refer to supporting information figure with fine resolution of fine spacing of key points, because a reviewer will ask it. You saw how Javid was curious. For spectra, description, in addition to just verbally describing what is seen in figures, one can make comments about observed wavelengths. So you were doing experiment with silicon, right? You were doing experiments with silicon. You STM. So what's color of silicon?
What color?
If you hold like big chunk of silicon in hands, how does it look like?
It will be transparent.
Huh? Silicon?
I don't
Did you, or your samples were too tiny that you were not
know.
seeing?
No, it was wafer, black.
Huh?
Black wafer.
Black? Yes, it is black. Black, it means that it absorbs up to like 1,000 nanometers everywhere. So anywhere in visible spectrum. And here you show that it starts absorbing only at 400. So yes, silicon looks like a graphite in the pencil. Very similar. It's like little shiny if it is polished. Okay. So why this big difference between bulk silicon and nanowires?
Because of the band gap.
Why band gap is different so much?
Quantum.
Right, quantum confinement. So just mention it when you will be writing this part. And general trends, how the density of states for one-dimensional systems look like for carbon nanotubes and any nanowires. So theoretically, they expected to have these unsymmetric features, right? So one can derive it. London observed it not long ago.
What now?
About 10 months ago, in the PChem course.
Oh, absorption spectrum?
No, not absorption spectra. The density of states for a particle in the box for three-dimensional box, two-dimensional box, one-dimensional box.
Oh, yeah.
And for if it is one-dimensional dose, it has specific feature. If it is two-dimensional, then it is expected to have steps, and if it is three-dimensional, it is expected to be like square root of energy, or whatever. Maybe like e to the power 3/2, some power that grows slower and slower. But there are ways to derive these equations, and it's like natural expectations. So in the figures, in this figure, I remember we were discussing it last time here. So just the main thing is notation. So when it is time to describe it, just tell that it is a little technical challenge and we need to be very clear about notations. And when describing the relaxation, it will be natural to express like how surprised we are to see that relaxation is very quick. And then tell, oh, okay, sure, because non-direct transitions. Yeah. Good figure, professional quality. Yeah, thank you for making this delta K comments. Here in the labels, one may relabel them, so do not skip. Even if you do not describe them, it would be very strange, like why the lowest transition is skipped. Because it is, if the system will luminesce, it will luminesce at this color. So 400 will be about blue, right? Have you ever seen blue silicon? Aaron may have seen. So Eric Hobby does synthesize. He doesn't synthesize nanowires, but he does synthesize quantum dots. If you synthesize quantum dot of like a couple of nanometers, they will emit blue. It's a synthetic challenge to make them, but it is possible to make blue silicon.
I think. I don't know, the samples they've been doing lately, the lowest they go is like 600.
Because of surface impurities, but it's an interesting feature, and it is a little too high, but it is not impossible because of the quantum confinement, because it is really tiny samples. Yeah, this table has potential for improvement. Maybe a range in the increase of energy, swap order, and then also several groups of transitions between peaks in density of states may contribute only to one optical transition. This is nothing wrong. There is a suggestion that one may or may not follow. Maybe it is better for supporting information. What if one places, so later on there are so many orbitals that look very similar to each other, as you will notice on the last meeting. So what if one picks up 8 orbitals that would correspond to the states and put them right into the figure to illustrate as an insight, because you already show them here in a very dense way, and one can still follow the patterns. So what if we take 8 lowest transition, Luma and Luma plus 1 for 4K points, and just paste them at the top of the blocks. So it could be, there is no big science in it, but it will be illustrative to show what we are doing and transitions between which states, how the band structure is formed. What is the opinion of everyone? Should one keep this super figure all together, or maybe separate dynamics and summary of dynamics as two different figures? Would it be any benefit to tell that this is like figure 4 and this is figure 5? Yes? So I don't care, it's just an opinion and possibility, because this is most important information in the whole paper, And typically, when journal goes through formatting, they put figure on the top of a page, and then your text goes after. And if you describe it for a long time, then figure will stay on page X, and your explanation will go to page X+1, X+2. So if you split it, one can like navigate reader to the figure easier.
This time the relaxation time figure is good. Do I need to change anything on this? The relaxation rate figure?
You will have some opinions about modifying it, so discuss it with him. I'm happy with how it looks this way.
Still, it looks suspicious to me because it is not consistent with the band gap structure, like the position of LUMO. Because right now it's like 0.2 electron volts, right? And if we go back to figure 2, it seems like it's 0.7 electron volts.
So it should be 0.6.
No, you should look at the
And then this will be
0.5.
like 0.3. Yes, this should be 0.6 instead of 0.2. Right, I see what you mean. Did you
Yes.
have it written?
Mhm.
Okay.
The other one is good.
Huh?
Or
Oh, for the summary for this lowest
Right.
panel,
no, I mean the right panel, top right one.
top right. Let's see. So here, this one. So this is about 0, right? And in figure 2, the LUMO is about 0.3. Well,
Okay,
I don't care much, but if I would do this figure, I would also remove this space because it doesn't carry any information, and also this space to focus only on the region where we have some noticeable dynamics. If you have energy to do changes. And this is probably not K sub E, it would be tau sub E, right? Nice data. Well, thanks much for having enough energy for this. Thanks. I remember myself when I was a postdoc, I was doing like, when I didn't know what to do, I was just plotting orbitals like 100 per day as a relaxation. Oh, any more comments to work by Fatima? Work by Aaron? I'm fine with figures for the main paper. For the table, I probably could put the prime symbols in a separate column because they are experiment. So, did you notice this? That A, B, C, and D are computation, and A prime, B prime, C prime, D prime are experiment. So there are 3 lines in figure 1C. So red is for computation, dashes are for experiment of a quantum dot 10 times larger than in computation. So if something corresponds, it's just a good luck. It's one cannot expect systems 10 times different to coincide. It's, if they would coincide, it would be cancellation of errors. So when, we can also only tell that we follow some general trends and features. But right? and the green line is density of excited states, which is same equation as for absorption spectrum, but with placing there one instead of oscillator strengths everywhere. So in some sense it would be like measure of degeneracy of each transition. I have no objections for this figure, although I can imagine that maybe you guys, someone in the audience did. But it is like first approach, rough approximation, the linear fit to some more complicated data sets, just to briefly describe what are the features. Fatima, it looks like you may have a comment.
Yeah.
So
I wrote it down here.
can you tell briefly?
So for the black one.
About black one?
Yeah. So you can divide two regions.
So you wanted to make it two separate
Fitting.
ranges. So one range it will be line with one slope, and another range it will be line with another slope.
Mhm.
Okay. One can either do it or just mention it as a possibility. So one can, it is what Fatima is doing. She's taking data set, breaks it on two different intervals, and apply different fitting equation for different intervals. So it's like
Energy ranges.
sequence of broken lines, which is justified that upon some threshold energy, the density of states or character of couplings drastically change, and one needs different fitting equation. I'm not 100% sure it is needed here, but it is an opportunity. I do not have objections to this figure, but anyone has? No. Okay. And I cannot judge this one because I'm emotionally attached to this figure.
And I haven't updated it since last time.
Huh?
I haven't run a new video yet.
Okay, that's fine. It's a lot of work.
Yeah, I'm just trying to find a computer that's not my laptop to run it on, because it's. I think I tried it on it one time, but the fan kicked on after like a minute.
I was running it on a laptop overnight,
Mm-hmm.
so it was about like 15 minutes per one time step, and sometimes it goes like this overnight ends at noon. Once again, many thanks to London for making breakthrough for reading part charges into MATLAB. It's your credit. Text. Well, there are minor comments, but nothing in principle. There is the thing that. So it is. Discussion of excited state density of states in a paper by Aaron. And he's telling that transition from whole orbital with one lobe envelope function S whole to S for electron gives the largest transition, which is expected and very correct. But in addition, one can make additional observations that if the symmetry of the envelope function for electron and hole stays the same, like S to S, P to P, D to D, it is expected to have favorable selection rules, while if it is change of the symmetry of envelope from S to P or P to S, it is expected to be unfavorable. And for spherical quantum dots, it was popular subject for like dozens or hundreds of papers for the last 20 years. So it's people will not stay cold-blooded if you introduce this discussion. So it will, good or bad, but it will attract attention and readers to whatever you write. So it is a thing that we discussed between Aaron and London about 15 minutes ago. So it is spin conserving and spin violating transitions that make this pattern of alternating height. And this is the thing that we already discussed in connection to Daniel's work. So many of us are defining dissipation energy as energy of initially occupied orbital minus energy of LUMO or whatever. But one can just tell that it is expectation energy of electron at initial and final time. And it is a little bit more general. So what if one has excited several orbitals at initial time? But this would be kind of more general definition. More comments to writings by Aaron? No? Anything else to add to today's session? So I have a question: should we like push pedal to the metal and make next section on the next meeting, or better make another session on results, so that we make corrections, let results section grow, and go over it once again?
That one?
Huh?
Second option.
Second option? Yes?
I second that option.
Fatima? Second, okay, then we will do results section once again. So please, authors collect feedback, reviewers distribute feedback, and let's incorporate all comments. And these Tuesday meetings will not be continuously and solely on reviewing and paper writing. There will be a couple of collaborative meetings with different experimental groups, so that we have a little relaxation from continuous writing, and collaborators have chance to collaborate. Okay, meeting is done. Thanks much for staying over the time, and see you on Friday or maybe on some other occasion.